Hello. Today we have April Hendley from Southern Illinois University, a colleague of mine who will be talking on gamma ray bursts. And please, April, go ahead. Thank you.
Okay. Let's see. Okay, so let's see. We'll talk about gamma ray burst. Y'all hear me okay?
Yeah.
Yes.
Okay. So anyway, gamma ray bursts, they're related to supernovae. So I'm gonna go through some about supernovae first, and then talk more about how gamma ray bursts were discovered, basically what causes them, and a little bit about the mission that they met.
Mhm.
So anyway, like I said, talk about supernova first. The ones that's most connected with gamma ray burst are the type 1c. And there's two basic types of supernova, novae: carbon detonation, which is the 1As, and core collapse, which is everything else. This rest of the slide just shows the difference between all the different types. Basically anything that starts with 1 has we don't see any hydrogen, and when we look at the light from them, while the ones that begin with 2 have hydrogen. So
maybe I can slow you down a little bit. Could you explain supernova a little bit more?
I was going to explain on the next slide, next couple of slides, what causes them more.
Okay, all right. Yeah.
Okay. But for the most part, I'm not going to worry too much about all the different types. I'm just going to worry mostly about difference between carbon detonation and core collapse.
Mhm.
Oh, I guess the next slide isn't quite explaining them yet. This shows basically how they brighten. They don't reach peak brightness immediately. It takes about a week. And the one that we are most connected with gamma ray burst is 1C, which is also the same line as 1B on this. Okay, so different types. I'm gonna go with core collapse first and get it out, or not core collapse, carbon detonation first and get it out of the way, and then worry about core collapse. Carbon detonation, the ones that's not connected to gamma ray burst, are the ones that's also referred to as type 1A, and what they are is a carbon oxygen white dwarf that's gained too much mass. Basically, they've exceeded what's called the Chandrasekhar mass, which means they've got gained more than 1.4 solar masses. They can do that from either companion star or possibly 2 white dwarfs merging. Like if it's a companion star and they're close enough orbit, one star can transfer mass to the other star. Anyway, if the white dwarf gets too much mass, it can't support itself against gravity anymore. Up till then, it's been being supported by the electrons being squeezed together, basically. If they got squeezed anymore, they basically get smashed into protons and get mostly neutrons, but and up until 1.4 solar masses, the electrons resisted that. But once this white dwarf reaches 1.4 solar masses, it basically that no longer can prevent gravity from collapsing it further. And the core will collapse. As it collapses, it heats up, and carbon's undergoing fusion throughout the star at once. And basically the star blows up. Let's see, Lisa is like a lot of energy. It's about 10 to the 44th joules. Let's just say a lot. and you get a shock wave moving outward about roughly 0.03 times speed of light, and they're about 5 billion times brighter than the sun. The one thing with these type of supernovas, they all have about the same brightness, so we use them to get an estimate of distances to the galaxies they occurred in. Last thing on the slide applies to both this type of supernova and the core collapse. The light doesn't come from the explosion itself. In the explosion, you get basically nickel 56 produced, about half a solar mass. The M with the circle and dot means solar mass. Anyway, nickel 56 radioactive. It decays to cobalt 56, which is also radioactive, and it decays to iron 56. And the light from the supernova basically comes from that radioactive decay. Like I said, that applies to both carbon detonation and the core collapse supernovas. The core collapse supernova is formed basically by death of a massive star, roughly more than 8 times the mass of the sun. Anyway, star that massive can fuse a lot heavier elements in its core than our sun can. Our sun will fuse hydrogen to helium, and then helium to carbon, and that's basically it for our sun. A more massive star can fuse the carbon and so on until it finally fuses silicon to iron. Once it gets the iron core, it has a problem. It can't get energy out of iron by fission or fusion. Basically, to get iron to undergo either fission or fusion, you have to add energy to iron to get it to do one of those two. But you can't get energy out of the iron by fusion or fission, which means it suddenly loses its energy source and it can't support itself against gravity. Up until that point, the star supported itself against gravity because you have this hot, basically it's hot and it's trying to expand because it's so hot, while gravity was trying to pull it inward and there was balance. But whenever it get iron, like I said, you can't get energy out of iron. It can't support itself against gravity and the core collapses.
So can I ask a very tangent question here?
Okay.
Like, so all the other elements can be made by fusion, which happens inside the star, up till iron.
Yeah.
But beyond that, you cannot fuse anything to keep creating higher elements. That is what I'm hearing.
Well, you can't get energy out of them you can't get energy out of fusion past iron.
So by any chance, do you know like how the heavier elements are formed then?
I think some of them's formed in supernovae, some's in some reaction at the very end of the star's life. There's various methods on how some of them get formed, but but basically some of them get formed during the supernova itself.
And is it true that like, I mean, at the core of our Earth also, like there is some sort of radioactive
I think so.
reaction happening?
I think so, or I think there was at one point that generated some of the energy or heat that the core had. Whether it still has much going on, I really don't know for sure.
Okay. Yeah.
Okay, so I said the core can't support itself against gravity anymore, and it collapses. And it basically, more or less, collapses to a certain point. I almost want to compare it to hits bottom, picture like a ball being dropped and it bouncing. But basically collapses, hits bottom, and then basically rebounds back. And when it rebounds back, it basically slams into the outer layers of the star and basically blast them off. And during all that, you get the nickel 56 produced, which, like I said, decays to cobalt 56, which then decays to iron 56. You get ionized hydrogen and electrons recombining, and so. And the differences in the spectra and the light curves that we see with the core collapse is caused by stuff that's previously been ejected from the star or possibly some of the surrounding interstellar medium. Like if we don't see any hydrogen, that means the star has basically already lost most of the hydrogen in the outer envelopes that that's basically stars lose mass and expel the mass. And if we don't see any hydrogen, that means that's basically already been lost. And stars that's lost the helium, that means the helium's, we don't see helium in their spectrum. So, and anyway, most of the gamma ray bursts are associated with supernova, that's type 1c. If I go back for a second, type 1c is one that we don't see hydrogen or helium. So it's lost both the hydrogen and helium that was around the core.
Mhm. So once it collapses and ejects the outer layer out, what it becomes?
Well, after the supernova, the outer layers keep expanding and we see a supernova remnant. In the center part, what's left, if it's on the lower mass side, it becomes a neutron star, which is about the size of a metropolitan area.
Mhm.
And has a density like that of the atomic nucleus. And they spin very fast, like seconds, fractions of a second. Some of them even hundreds of a second, or and they also have very strong magnetic fields. If what's left is on the higher mass side, then we don't know of any force that will keep it from collapsing all the way currently. Then it becomes a black hole. Whether it actually collapses all the way to a singularity, though, well, that part, basically our physics will last until it gets very tiny, but not all the way to zero radius.
Mhm.
And though, since we can't get light or anything out of a black hole, it's kind of hard to actually see what happens inside. So, okay, so next is how gamma ray bursts were discovered. So, started 1963, the nuclear test ban treaty was signed. And in 1968, the US put a series of satellites called the Vela satellites into orbit. This is a photograph of one of them. And the Vela satellites, well, first of all, when someone detonates a nuclear weapon, it gives off a burst of gamma rays. So the job of the Vela satellites was to look for a burst of gamma rays coming from the ground to see if, basically watch for anybody testing a nuclear weapon. But the Vela satellites started detecting gamma ray bursts, all right, about one a day from space. Since it was a military thing, the data was classified initially. It was 1973 before the data was declassified. However, for the next 22 years, it wasn't certain where the gamma ray bursts were coming from, what produced them. Basically, we could get a general area of the sky where one came from, but we couldn't localize exactly where that one came from. It was still over a large area. What we could do was get them, each individual one reduced to a small enough area that we could get kind of an overall distribution on the sky. And this is from one satellite called Burst and Transient Source Experiments was on Compton Gamma Ray Observatory. And basically shows, whoops, I don't know what I hit, but basically it shows the distribution overall on the sky. And there was no certain area on the sky where they were localized that seemed to be more uniformly distributed, which led them to conclude it was either something like the galactic halo that surrounds our galaxy, or other galaxies at cosmological distances. It actually turned out to be the other galaxies at cosmological distances. But like I said, didn't know that for about 22 years till after the data was declassified or so.
So on this slide, like, what is the relevance of nuclear test ban treaty and sending the satellite in the sky?
Well, those VLS satellites is how was what first detected the gamma ray burst from coming from space. And they were basically put up to watch for someone violating the nuclear test ban treaty.
Okay.
In other words, if the treaty hadn't been signed and the US hadn't put up the satellites, might have been longer before we discovered gamma ray burst.
Okay.
Okay. So anyway, about 1997, we could start pinpointing the locations enough that we could find host galaxies, the redshifts. That was mainly due to a satellite called Beppo-Sachs, basically finding the X-ray afterglows. And since we can get, basically we can get the image, resolve images and stuff in X-ray better than gamma rays, we could get a better location. So once we could get the X-ray afterglows and get the locations, we started being able to find radio and optical afterglows. So, and eventually we could find, like I said, the host galaxies, and eventually we could even find, like if there was a company Supernova, we could find that too. So, Burst Alert Telescope on board Swift basically allow faster localizations, earlier afterglows. Could find the short gamma burst afterglows. Talk about what that means by short in a bit. There's two broad categories of gamma ray burst. Let's see, gamma ray burst monitor on board Fermi, which is X-ray satellite or X-ray telescope. Anyway, it could get very high energy behavior. Basically, this thing, sorry, I just realized this doesn't quite fit in my habit, but gamma ray burst can release much energy in 1 second, sun will in its entire lifetime. Okay. So this slide, don't worry about the actual numbers here. The thing I want to just point out is, like, say this one, like how it has just single spike, while this one has a bunch of spikes. So there's variation in that. You can see over here, they vary in the number of spikes too. The time, the duration, some are really short, some are a lot longer. Some, this is terms of counts. Some are brighter, some are dimmer. There's quite a bit of variation in how bright, how long.
What's on the vertical axis here?
Like,
ME.
It's basically intensity, like counts per second.
Okay.
So
So why it is so low in the bottom one?
just it varies from burst to burst. So and this one, it may turn out to be overall, like, since it's longer drawn out, it could be more similar overall, just longer drawn out. It's just,
Okay.
there's just a bunch of variability between them.
Mhm.
So there were some patterns. So okay. This here shows, this is for one burst. And you see the difference in the different parts of the spectrum too, for just the prompt for the actual gamma ray burst itself emission,
Mhm.
the afterglow. So it can even vary in different parts of the spectrum. Okay. So anyway, the thing I was most interested in is basically how we get the gamma ray bursts. Basically what causes them.
Mhm.
Anyway, gamma ray bursts are divided into two categories. It's based on their duration. The long bursts, which have durations greater than 2 seconds, and short bursts with durations less than 2 seconds. So it's basically the dividing line's 2 seconds. It's kind of there's some debate about whether that's the most appropriate place to put the dividing line, because it like, could it be a bit above 2, a bit below 2? So the 2 just kind of, some people say somewhat arbitrary of the second choice of 2 seconds to divide them. So, but anyway, we think that two categories in general are caused by two different progenitors. There's also a possible third class with ultra long gamma ray bursts whose durations are longer than 10,000 seconds. Some other differences between them, and all this goes to what causes them. The short bursts tend to be harder, higher energy photons, but less energetic overall. And the afterglows for short bursts tend to be fainter. So short bursts tend to be higher energy photons, but less energetic. The long bursts tend to be lower energy photons, but overall more energetic when you look at how much over an entire event. So, the redshifts of short bursts, where you get the redshifts tend to be lower than the long bursts. That means the short bursts tend to be closer to us. So, long bursts generally occur in galaxies with ongoing star formation. The regular galaxies, some spiral galaxies, and they generally occur closer to the areas with the ongoing star formation. While the short bursts tend to occur in galaxies, both some with ongoing star formation, but a lot of times on ones without ongoing star formation, including elliptical galaxies. They also tend to be, or they also can be significantly offset from the host galaxy, basically outside the visible host galaxy. What this means, or what this indicates, is that the long bursts are basically related to something that occurs like with stars that's not very long lived or something like that. While the short burst, if it's something to do with stars, could be stars that's a lot longer lived, that's gotten basically no longer in areas with ongoing star formation. Example of what I mean is the most massive stars will live their entire lives and still be fairly close to where they formed in areas with ongoing star formation. Low mass stars, they live so much longer that they, by the time they end their lives, they may not be in the same area where they formed at all. They could be an area that had little star formation. So. Or in the case like elliptical galaxy, a galaxy that no longer has an active star formation. Okay.
So basically, the galaxies that are already formed, if you were looking from a star like a gamma ray burst coming from those galaxies, they will be all long, most likely, right?
Well, if it's like spiral irregular, where there's new stars still, where there's new star formation going on, we can get the long ones. The short ones would be galaxies like more like ellipticals, or where there's no new star formation, where it's just stars that's just getting older. Well, you have the longer.
Oh, so longer ones are when the ongoing star formation is happening.
Yeah. Well, the short ones can be where there's ongoing star formation, but they also occur in places where there's not.
Isn't it like slightly confusing here, because the gamma ray burst is on the cycle of basically when the stars are towards the end of their cycle, right?
One type. That's the thing. The long bursts fall in that. The short bursts actually are different. So,
Okay.
So the long burst, sometimes it's called Thalassery or Hypernova. They're basically a massive star that reaches the end of its life. Generally, a massive, what's called Wolf-Rayet star that's lost the hydrogen helium envelopes. Basically, a Wolf-Rayet star is more than about 25 times the mass of the sun. It's one of the most massive type stars, O stars. And the Wolf-Rayet stars lost its hydrogen and, like I said, the helium too. Anyway, at the end of its life, when it runs out of fuel completely, basically when it gets the iron core, it becomes either type 1b or type 1c supernova. Anyway, once the supernova happens, the core collapses to a black hole, and the black hole accretes matter initially at a rate about a solar mass per second. And the amount of time it accretes matter at that rate is basically comparable to how long the gamma ray burst lasts. So, anyway, you have accretion, interaction with magnetic fields. You get this collimated outflow. The other possibility people have given is basically neutrinos, and neutrinos annihilating produces photons, electrons, positrons, and so, and basically eventually somehow producing a relativistic jet. So that jet penetrates the outer layers of the star and eventually interacts with the interstellar medium. The afterglow is produced when it interacts with the interstellar medium. The prompt emission, the gamma ray burst itself, is basically occurs before then, when with the interactions before that, like with the star and with the jet itself, there's interaction. There's basically they call them internal shocks inside the jet that goes on. If you're looking at one of these stars along the equator, you'd see a more normal 1C supernova usually. In fact, along the equator, you might not see the gamma ray burst. So the one for massive stars here, you have the massive star, the core collapse, the black hole, and the accretion disk, and then you get the jet. And you get inside the jet these shock blobs, some moving faster, some moving slower. They collide with each other. You get internal shocks, and you get the gamma ray burst. from that. Then the material is moving relativistic speeds, eventually runs into the interstellar medium, get more shocks, what's called external shocks, and that produces the afterglow. And since it's slowing down over time, the afterglow tends to start off in the X-rays and eventually become longer and longer wavelengths. So it's kind of, the radio tends to be at the later part of the
Spectrum, yeah.
afterglow. So
But so the point is on that figure, like, I mean, are you saying that as it goes from gamma ray emission to afterglow, like all the gamma rays will be like, I don't know, like I think I mean to say,
at the very beginning of the afterglow, you can get gamma ray afterglow too, and then you get the X-rays. But so
like, so these are basically photon, right? Very high energy photons. What are they colliding with to generate the lower energy photons or something? Like, how are they creating the X-rays or like later parts of the spectrum?
I think of this, besides the photons, you also still have material itself, electrons, photons and stuff
Mhm.
moving outward. That's
Mm.
crashing into basically the medium surrounding the star, the stuff that started ejected earlier before it went supernova.
Hmm.
Or if it's an area that's dusty in space, where you have dense enough interstellar medium around it, they could be crashing into that and basically just them running into that stuff. So you get, let's see, synchrotron,
Mhm.
there's something inverse Compton or something, and
So is it okay to say that the very massive stars which are going to turn into black holes, you will never get the very high energetic gamma ray burst from them? It will always be like the later part of the spectrum? Or like, am I like missing something? Like the picture is kind of showing in such a fashion that there is a very high energetic gamma ray burst, but eventually they will die down and it will be like lower.
I think of here, like this part here is occurring earlier in time than this part.
Hmm.
So this part that would be emitted before the material had reached this far out. Basically, this is, as you go left to right, it's basically time's increasing too.
Yeah.
So in other words, the gamma ray burst here might be able to escape before the material runs into the interstellar medium and produces the afterglow.
Oh, I see, I see. Okay. Mhm.
The next couple of slides is some of the long bursts and evidence they are connected, some evidence they are connected to supernova. There's been, going to look at one in particular, there's been other ones since that shows a connection to supernova, but this is one gamma ray burst 030329. It occurred March 29, 2003. Anyway, these curves here, the dashed one would be for basically just the gamma ray burst afterglow itself, how much light it puts out. So it's basically, you can think intensity versus number of days. This curve, the dotted one, is a supernova. They're using a similar, what they think of as a similar think would be a similar supernova, and adding the two together, and basically it fit the light curve for the gamma ray burst afterglow. In other words, basically the afterglow from this gamma ray burst looked like what they think of the typical afterglow plus a supernova. So
Mhm.
they also, same one, looked at spectrum. They basically took the spectrum about 10 days and subtracted the spectrum about 6 days. And got this and compared it to other supernovas. Or another supernova at 2 different times, and it looks fairly similar in shape. So the reason why they took one day minus the others, the one they subtracted was mostly just the continuum before it showed much evidence of the supernova. So they wanted to try to subtract out the gamma ray burst afterglow part and just get the emission from the supernova.
Mhm.
Okay. So short gamma ray bursts. I think instead of being a death of a massive star, they're either 2 neutron stars merging or a neutron star and a black hole merging. So you have the 2 neutron stars in orbit, they lose energy, the orbits decay. Eventually the lower mass one gets disrupted. Those mass on a higher mass neutron star, eventually they merge, form a black hole. You get magnetic field gets intensified, you get a relativistic jet, like you did for the other type of gamma ray burst. It's just in this case, since we don't see a supernova accompanying it. And the energy is, like I said, tends to be high energy photons, though the overall energy tends to be less, but the photons that we do get are generally higher energy. So this here on the bottom is basically from LIGO. Anyway, they observed a gamma ray signal here. This was August 17th, 2017, from a couple of merging neutron stars. 1.74 seconds later, they detected a gamma ray burst. And the time difference between the gravitational waves and the gamma ray burst basically corresponds to what they think, at least what the theoretical delay would be, closely enough that basically it seemed to fit models for that. So this is the top 3 are the gamma ray bursts. So, and just like the other ones, the peak is slightly different for different parts of the spectrum.
Mhm.
Not only that, the gamma ray or the gravitational wave basically narrowed it down to this little green area in its location.
Mhm.
The gamma ray burst, the location more or less narrowed it down to the purple area. And then they detected an optical transient, basically like the visible light from the supernova. And the optical transient is a star here. And they also found a host galaxy too, that all basically lined up or were consistent with their location.
So this is just one star. That is what you're saying, like the optical spectrum that was observed. That was only from one star.
Yeah, like this was here all from one short gamma ray burst, and this is, like I said, the purple is that gamma ray burst, and the yellow dot is basically the optical light from it, basically the supernova part.
Interesting. Okay. So you're saying that this particular thing, like the galaxy was not known before.
Now the galaxy, I think with it having this catalog number, the galaxy was known before, but the optical transient and all this lined up more or less with this galaxy too, but there could be a number of galaxies in the purple area for sure. And even the green area even covers enough. There could be several green areas. It's just the optical transients where this yellow star is.
Mhm.
It's just that everything at least fit in the same, had overlap and where they were, so.
So question, when there is so much error in the gamma ray detection, is that because of the device we are using, or is it just that gamma ray burst seems to be so much across in the sky?
It's more, I'd say, have to do with probably the gamma rays themselves. For everything from radio to X-rays, you can get true images with a telescope. Like you can bring the light to focus on the CCD. Gamma rays, we can't really get true images. Like if you try to have just a curved mirror and you try to send the gamma rays, try to bounce it off of a curved mirror like we'd use in the optical telescope, gamma rays would just go straight through. So do X-rays for that matter. For X-rays, we can use cylindrical mirrors, basically nested cylindrical mirrors that's at very slight angles. Because if the basically if they're at an angle like that and the gamma ray comes in or the X-ray comes in at a shown angle, try that again. It can bounce off some and come, and you have nested ones, and you can bring X-rays to a focus that way. Because you'll have like another one, they'll basically be kind of cylindrical. And the X-rays will bounce off at that angle, but they won't. If you send it more and more normal to the mirror, the X-rays would go through. But the gamma rays, that doesn't even work. So, in other words, it's part of a lot of the problem they had finding and still do finding location just based on the gamma rays is the fact you can't really get true images. So,
Okay. Thanks.
Okay. One thing about this gamma ray burst that was associated with this gravitational wave was it was the closest burst that had been observed, but it was also weaker than normal, which leads to some questions about what was going on there. Question is, could it be intrinsic and we just happened to detect it was because it was close, or could the jet have some structure and it depend on our viewing angle? Like, are we viewing the side of the jet instead of straight on? Is the jet to where it's more intense, basically with, let's say, more intense or denser at the center and not as much at the edges, and we're seeing it edge? Or could there be some material forming some type of cocoon around the jet and we're seeing that more instead? So I'm trying to think if I don't remember when I looked up stuff recently whether there'd been, I don't remember seeing anything about another one detected gravitational waves yet, but I don't think they've detected, if there has been one, there hasn't been too many at all. So I don't remember seeing one when I was looking at more recent research recently. Okay. So I'll go forward for a second right here. So this is for the merging neutron stars, get the black hole, still get accretion disk, just no supernova, and you still get the jet. So this would be basically the short gamma ray. path on this diagram. Okay, so there was a possible long class of gamma ray bursts with durations larger than 10,000 seconds. Anyway, one that had duration that long had a supernova that was 3 times more luminous than typical supernova, and also spectrum was different. One of the proposed possible progenitors was called magnetar, which very strongly magnetized neutron star. And the possible theory on that would be you have the massive star collapse, you get the magnetar and the supernova. Magnetar then re-energizes the ejecta, and you get a longer and brighter supernova. Oh, like that's this here is more uncertain than the previous one, than the short and long ones on the previous slides.
But they have been observed, right? Like basically you're saying that the intensity for more than 10,000 seconds from single source has been observed, right?
Yeah, some have been. I don't think too many's been this bright, but it's still fairly.
So what is actually the confusion here? Like, I mean, you said that like there are, it's not like, so basically it is not known that it is from the magnetized one, or like what is the
It's combination of that and the fact that I think they're more enough recent that they still are coming up with explanations.
so source is not certain.
Yeah. So it took a while after they started localizing the other gamma ray bursts before they ended up getting a good idea on what sources on them. So
You had a question, Shajesh?
No, I'm good. Thanks.
okay. As for the mission itself, you get this a newly formed black hole, and following rotating debris. You get debris that gets ejected and a jet along the rotation axis. You get magnetic fields, couple of debris to the black hole, get rotational energy from the black hole pumping in a jet. And the jet becomes highly relativistic and basically collimated. And then, like I said, it slams into the, or runs into what was the outer part of the star, and then into the what was surrounding the star. Energy is initially a form of kinetic energy. You get these internal and external shocks, basically the internal different parts of it moving different speeds and running into each other. And the external, when it starts running into the stuff surrounding the star. And then electrons moving across the shock will get accelerated relativistic speeds. You get non-thermal emission, they interact with magnetic fields, each other, photons basically synchrotron, what is it? I'm trying to remember, inverse Compton, and I took a picture of my screen earlier so I'd remember. Because I get slightly confused, inverse Compton and something synchrotron self-Compton. I get confused on the two Comptons sometimes. So, but anyway, you get, so the prompt emissions from the internal shocks and the afterglows from the external shocks, and eventually jet slows down, loses energy, and you get X-rays, optical, radio, and poly in between X-rays and optical, poly ultraviolet, and also infrared in between the optical and radio. So, and that is actually it. Any questions?
I mean, I was asking in the meantime, middle, so I think if we just discuss something, then probably something comes out more naturally.
So would it be correct to say that uh like supernova is used to measure distances?
Type 1A supernovas used to measure distances.
Oh, and these are from 1C, is it?
Yeah, they're not used to measure distances so much.
I see, I
To
see.
get the distances for these, they had to be able to get them localized enough to find the host galaxy. Then they could get distances from that.
Okay,
So
okay. So my question is not even there. Yeah.
the 1Cs can have different brightnesses. 1As all have about the same brightness.
Yeah, that answers, because I was going to ask that how come they are able to measure distances when there is not a clarity on.
So whenever they observe like these 1C emissions, like it's not like they're coming in. I mean, is it quite clear that these gamma ray bursts, whenever they're observed, they're coming only from one source? And it is not that like it is just one star doing it, but multiple stars in the galaxy are sending out the bursts.
Yeah, they're fairly sure it's only one star. I'll go back. Actually, this slide will work.
Mhm.
It has to do with how spiky these things can be.
Hmm.
Like how it fluctuates rapidly with the brightness.
Hmm.
That gives an maximum limit to their size. Because the light of something can, in some astronomical object, can only fluctuate as fast as light can travel across it. So if it takes light 1 second to travel across the source, that's the fastest it can fluctuate in terms of its luminosity. So basically, because of how fast they can change the light output, that says they have to be fairly small.
Source, okay. So can you show me another example where you cannot say that it is it's from one source, it could be from multiple sources?
You mean
like a graph of the same kind, like right now you said that the peak, like narrow peak, decides that whether it is a one source or not a one source, but do you have another graph which shows a broader peak or something where you can surely say that it is not from one source?
not that I can say surely. The broadest one I have is just this one. You still have the spikes, or this one's just 10 seconds. So from here, that's 10 seconds to 0.
So does it say something like, I mean, can you from there you cannot conclude that it is from one source? It could be multiple sources.
Yeah, well, that would still have to be about something that's at most probably 10 light seconds across. So that's still, I don't know, takes 8 minutes for light to reach us from the sun. So
What's the size of sun in light seconds? Or
I don't know on that one how long it takes to cross light for. I don't know how long it take in terms of light seconds for the sun across the sun. So,
Mhm.
but
Like yeah, go ahead, Shajesh.
what I'm saying it basically, if this is roughly 10 light seconds, it's still be probably smaller than Mercury's orbit for sure, which so
Which is still can be just one source, sun, one star.
yeah, because there's stars that's basically about as big as our orbit.
Like the way I am thinking is that, like, see, the most galaxies are formed, like most stars in the galaxies are formed during the same time, right? So they're aging the same way, most likely. there will be like numerous stars in a galaxy that might be going through the process of this uh, supernova formation, or like, I mean, a gamma ray burst or something. And if you are observing it, like suppose the telescopes are pointed in the direction they're collecting data, like how do you distinguish whether this is coming from multiple stars in a galaxy, or it's just
Partly they're probably using nearby galaxies, the supernova rate, to get an idea of how many is likely at any one time. I mean, I'm gonna say, if just looking at our galaxy, it was like, well, the last one that occurred in our galaxy was like Kepler's, I think Kepler's supernova, so that we know of. So, and like if they look at Andromeda, they can see the rate of it and other ones. So it'd be, well, I wouldn't say it's impossible to have a couple of stars at the same time.
Mhm.
It's just based on what we can see with the galaxies nearby and supernova in general, and the galaxies that we can see in galaxies is just not that likely. So this rate of supernova is just
Hmm.
So from what I gather, would it be correct to say that the area under these curves give a measure of the mass of the star that was dying?
I say, I'm trying to think if, because the area under the curve would probably be overall luminosity of the gamma ray burst, and that may not correspond to the actual mass if there's enough.
Because there will be dust released also, right? A lot of matter particles will be out.
If they lost enough mass before they went supernova and we had the gamma ray burst, then that wouldn't be as, then some of that dust could obscure it, and it wouldn't be as bright.
I see. Okay. Yeah, very interesting.
Yeah, interesting, but I get confused also a lot with the galaxy formations basically. So when the nebula, eventually when the stars die, they create the planetary nebulas, right? Or like nebula basically, where the star formations will begin again.
The planetary nebula is like lower mass stars,
Mhm.
and that material will eventually get mixed in a stellar medium, but I'll say it expands slowly enough that it'll be a while before it gets incorporated into a new star. So
Yeah, like I mean, just like I mean, I'm just trying to like understand the fact of for galaxies, we say that almost all galaxies have a black hole at the center of that, which means that they are probably coming from the earlier supernova, somewhere where the black hole actually formed a supermassive star when it collapsed and created the supernova, and then it got the formed the black hole. I don't know, like I get always confused, like because each galaxy has like millions of stars, right?
yeah, keep in mind, they also don't really know how the galaxies get the black holes at the center. And generally, a lot of times they're regarded as separate entities from the stellar mass black holes.
Hmm.
So there's even black holes somewhere that's in the like tens of thousands of solar masses, and they really intermediate mass black holes, and they really don't know yeah, how they formed either. So,
Mhm.
I mean, there's a lot of things that's still unanswered.
Lots of uncertainties.
Yeah.
And the point is, like, when we talk in terms of like death of stars, I mean, galaxy, again, the galaxy has millions of stars, and they are formed around the same time, roughly the same time, probably be dying around the same time also. Like, this could be on a span of millions of years, but it is around the same time they are dying. And most of them will go supernova, right?
Most stars are going to end like the sun, just as a planetary nebula, just kind of, as they say, kind of with a whimper rather than a bang.
Yeah, yeah.
Ones that blow up in supernova are the rare stars. Maybe what I think it's like 1 in 10,000 stars fall into that massive star category.
Yeah, but it's still, one galaxy will have multiples of them.
Yeah, but like I said, they can look at galaxies and since we see supernova in other galaxies, they get an idea of how often a supernova occurs. So when it's
Mhm.
and keep in mind, but we want to think that at the same, close to the same time. The other thing to keep in mind is in terms of stars, 500,000 years is a short time period.
Yeah, no, I agree. I mean, that's why I'm saying, like, the birth and death all are happening in millions of years time period. But
Yeah,
then again, I was thinking, like, there should be multiple supernova in a galaxy.
yeah, but I was gonna say, you might have once every few thousand years in a galaxy, but for us, that seems long. For a galaxy, that's short, or for a star, that's short, so.
Mhm. Yeah. It's interesting, actually, all this stuff. At least the observational astronomy is
Mm.
pretty.
Yes. Thank you, April. I'm going to stop the recording, but we can have the conversations going.
Okay.